Okay, so today we're going to talk about work and power, which are relatively simple concepts in physics, but they're also ones that I know in year 9 and 10 that students seem to struggle with when they're first introduced to them. We're going to do a little bit of maths today, fairly simple maths, but more important than being able to carry out the maths, which I think you guys are generally very good at, is having an understanding of what these quantities mean. So our keywords: work or work done, and power. So let's start with something simple that I know you're all going to be happy with, which is energy comes in lots of different types. And we should be familiar with all these things that are popping up onto the screen now: sound energy, light energy, thermal or heat energy, chemical energy, elastic potential, electrical energy. Some of these are stores of energy. For example, chemical energy is a store of energy, while some of them are energy kind of in transition. So light is energy moving as waves from the place in which they're produced to the place they get detected. Now I'm going to add one extra here that I didn't, when I, at least the classes I was teaching in year 9, that I didn't introduce. Sorry, that one should already have been up. Gravitational potential energy, that's a store of energy, uh, is nuclear energy. Okay, now nuclear energy is the energy stored in mass. I've written E equals mc squared there to say that actually sometimes you might not realize there is energy somewhere, but anything that has mass contains energy stored inside it. We know that hopefully from doing our work on nuclear fission, and that energy can be released if we destroy a tiny bit of mass and turn it into energy. So I'm going to add nuclear energy into that now as another type. Okay, so energy comes in all these different types, and we hopefully are aware of the fact that energy is always conserved, so you can't create energy or destroy energy. But what you can do with energy is you can transfer it from one type into another. So, for example, a light bulb converts the electrical energy that we supply it with into light energy, and along the way, it also wastes energy as heat and light. So we generally have useful forms and we have wasted forms. Okay, but always the amount of energy you put into any device is equal to the amount you get out. It's just about how much of it goes into useful forms. And obviously, a week or two ago, we were dealing with efficiency, and we've talked a bit about that already. So, some common energy transfers that you should be aware of: batteries turn chemical energy into electrical energy. I'm just showing the useful energy here. There's always going to be waste of some kind. In a battery, it's going to be heat. We've got a motor, like an electrical fan. So it runs on electrical energy and it turns it into kinetic as it spins around. In this case, the wasted energies would probably be sound and heat. A dynamo does the opposite job to a motor, where it turns kinetic energy from example, for the wind in a wind turbine into electrical energy. There's always going to be some losses again, probably heat and sound in this case. We've got solar cells, which convert sunlight energy into electrical energy. So these are all energy transfers. Okay, hopefully they're all devices you're familiar with. Okay, and they're all changing energy from one form into another. So if I ever mention energy transfers in the rest of this lesson, I mean energy being changed from one form into another. Okay, now there are different ways in which you can transfer energy. For example, you can transfer energy electrically. You could set up an electrical circuit and you could have resistors and bulbs that transfer electrical energy into light or heat or whatever. But one of the most common ways of transferring energy is to use a force. Okay, and when a force is used to transfer energy, we say that work is done. Okay, so if I ever talk about work and work done, I mean the transfer of energy, okay, by a force. So work done is the amount of energy transferred by a force. Now, this is probably the most badly remembered or understood part of the GCSE syllabus. You know, I've got students as well in my year 12, 13 classes who constantly make mistakes misunderstanding what work done is. It's very simple. Work done is energy. Okay, it's the energy transferred by a force. So, for example, it's a pretty dull example. Sorry, I could have used something a bit more imaginative. You've got a box like the one on the board, and you push it with force F. Now, when you push it with force F, you're transferring energy to that block. And if you use a force to transfer energy to an object, you have done work. And the amount of work that you've done, or the amount of energy you've transferred, because work done and energy transferred are the same thing, okay, can be calculated very easily. Okay, and this is hopefully an equation you can remember, at least now that you've seen it from last year. Work done, or the amount of energy transferred, is equal to the force times the distance moved in the direction of the force. Okay, now at GCSE level, the force and the distance are always going to be in the same direction. You look at the diagram here, the force is acting left to right, the distance is acting left to right. Occasionally there's examples where those two forces are not the two vectors are not lined up. So here the force is lined up with the distance. Sometimes you push in one direction, the object moves in a slightly different direction. If that's the case, we can't use this formula. We have to adapt it a bit. But at GCSE level, you're always going to get formula where the force and the distance are acting in the same direction. Now notice, the work is measured in joules because work is just energy. I sometimes think calling it work actually causes some of the confusion here. If we just called it energy transferred, I don't think we'd have as much problem. So work is energy transferred, and the energy transferred is just equal to the force times the distance moved. Most of the examples you're going to get involving work done are going to be very simple. For example, a weightlifter. Let's say a weightlifter produces a 3,000 Newton force to lift a weight 2 meters from the ground. How much work do they do? Well, the reason that the weightlifter would use a 3,000 Newton force to lift the weight is because the weight must weigh 3,000 Newton. So generally, to know the force that they have to pull with, you just need to know the weight of the actual object. So if he pulls on it with 3,000 Newtons to get it lifted, it must weigh about 3,000 Newtons. So how much work must the weightlifter do? Well, work is force times distance. So force times distance, 3,000 times 2, 6,000 joules. So basically, I've worked out that he needs to put 6,000 joules of energy in order to lift up that weight. So that's all work done is, the energy transferred by a force. Okay. Sometimes energy is not transferred by a force. You know, when a solar cells on a calculator turn light energy into electrical energy, you can't use work done there because there's no obvious force that you're able to use in your calculation. Okay, but in lots of examples where you pick things up, particularly, okay, then work done can be calculated as the force times the distance. Now, in this case, that work done is going to be equal to the gravitational potential energy gained by that weight. So you're doing work against gravity. So if he puts in 6,000 joules of energy, then that weight has now got 6,000 joules of extra gravitational potential energy in this case. So when you lift things against gravity, the work you do is just turned into extra gravitational potential energy. Okay, so key thing to get from this, work is the same as energy transferred. Okay, they both mean the same thing, but work is the amount of energy transferred by a force. Okay, and we've got this formula here which you need to use in calculations. Let's do a slightly harder example of this. Okay, so I've put it into a triangle here. I know that a lot of you guys are going to remember these from last year where you had to learn about 6 or 7 energy triangles for your end of year test or your end of unit test as well. So W is work, F is force, D is distance. Okay, as long as you get W on top of the triangle, it doesn't matter which way F and D go round. Okay, so here's the question. A car is moving with a kinetic energy of 200 kilojoules. Remember, kilo is 1,000, so 200,000 joules of energy, kinetic energy. It applies the brakes evenly over a distance of 20 meters until it's stopped. So you've got a car whizzing along, okay, with quite a lot of kinetic energy, puts the brakes on, and in 20 meters it's stopped. Now you've got 2 things I want you to figure out for me. How much work has to be done to stop the car? And then what's the average force that needs to be applied to stop the car in 20 meters? That force will be applied by the brakes. So I would like you to just pause for a moment and have a think about these questions yourself. I'll go through the answers in a moment, but over to you. Okay, hopefully you've had a go at that now. Now for part A, I'm guessing a lot of you have tried doing all kinds of calculations for this. You don't actually need to do any calculation here, okay? The car has got 200,000 joules of kinetic energy. Now, if we stop the car, we've got to remove all of the 200,000 joules of energy. We've got to turn it from kinetic into other types of energy, like heat and sound, because that's basically what happens in brake pads. Brake pads convert kinetic movement energy into other types. So we need to transfer 200,000 joules of energy away from the motion of the car. So therefore, we need to do 200,000 joules of work on the car. Okay, because remember, work done is energy transferred. the brakes have to remove 200,000 joules of energy from the car. Therefore, they have to do 200,000 joules of work on the car. Okay, so quite often they catch you out a little bit with this. You're expecting to do a calculation, but sometimes the answer is there already. A bit like with the gravitational potential energy and kinetic energy questions. If you know that an object has 100 joules of gravitational potential energy when you drop it, when it hits the ground, there's a chance that if in the right situation, that will be the same number as the kinetic energy when it hits the ground. Anyway, calculate the average force that needs to be applied to stop the car in 20 meters. Well, we can see from the triangle, force is equal to work done divided by distance. Okay, we've got our work done here. We've just got to remember to convert it into joules, and we've got a 20-meter distance. So we're going to do 200,000 divided by 20, and that leaves us with 10,000. It's a force, so it's measured in newtons. So therefore, that car would have to produce a 10,000 Newton force, which is quite a large force there, in order to stop it in 20 meters. Okay, if it wanted to stop it in 10 meters, it would need an even greater force. If it wanted to stop it in 100 meters, it would need a lower force. But however long the distance is that it wants to stop in, it's always got to remove the same amount of energy. It's got to go from 200 kilojoules to nothing. Okay, so that's basically what work done is. Work done is energy transferred, and you need to be able to use this formula. Okay, the other part of this lesson is going to be about power. Okay, because power in the English language basically kind of means how strong or how much influence you've got on people. But in physics, it means something different. In physics, power means the rate at which energy is transferred. Now, whenever we use that word rate, we're talking about how quickly. So the energy transferred per unit time. Okay, so power is how quickly energy is transferred or how quickly work is done. Because remember, energy transferred and work done, exactly the same things. So how quickly work is done or how quickly energy is transferred. So we have this formula that we're going to use. Power is energy or work divided by time taken. So there's kind of two triangles you can choose to use for this, because they're both the same. It just depends whether you want to use energy transferred or you want to use work done here. Okay, because both of them are the same. So I've got power equals energy transferred over time taken, or power equals work done over time taken. Okay, so let's do an example of using this equation. Okay, this is the mountain. You've probably seen him on Game of Thrones. He was the world's strongest man for a few years, but recently he broke the world record for the deadlift, which is basically when you just pick up a super heavy weight and you just lift it up until your back is straight. Okay, so you can look at, if you want to find this, you can find the internet, I'm sure, on YouTube. But he lifts 501 kilograms. Okay, so what's that? That's like six times my weight. So he can lift that to a height of about 80 centimeters off the floor. Okay, so he's only lifting it to like waist height. Now, the whole process took about 2 seconds to get there. So I want to know what his power output is. How much energy does he transfer every second? Now, we've got two equations we've got to use here. This is a two-part process, because we need to work out how much work he does first, or how much energy he transfers, and then we need to use that to work out the power. So the first step, let's work out how much energy or work he does. So work done or energy transferred is force times distance. Now, they've given me the mass. So if I want to know how much force he needs to apply, it's going to be the weight. Okay, because if I lift up a 1 kilogram bag, I need to apply 10 newtons to lift it, because the weight of a 1 kilogram mass is 10 newtons. So I've times 101 kilograms by 10 to convert it from a mass into a weight. Okay, obviously, if I'm being really picky, maybe I'd times it by 9.81, which is the value of the gravitational field strength. But we're going to just round it to 10 for now. So 5,010 newtons is the force he has to apply. He lifts it 80 centimeters, which is 0.8 meters. And so the amount of energy he transfers in that 2-second event is 4,008 joules. Okay, so 4,008 joules is the energy he transfers, which is his work done. Okay, and then once we've got the work done, we're just going to say, well, power is work over time. So we take the work done that he's done and we divide it by the time he's taken, which was 2 seconds, and we get a power of 2004 watts. Okay, that means a watt basically means the energy used in 1 second. So it means every second he's using 2004 joules of energy. So anytime you see a watt, it means joules per second. So if you put your microwave on the 8,000 watt setting, it means that it's converting 8,000 joules of electrical energy, okay, into kind of microwave light energy every second. If you plug in an 8-watt light bulb, then it's converting 8 joules of electrical energy into light and heat every second. Okay. Now, just one other thing I want to bring to your attention here. Okay, this work done equation that we've used. Remember earlier I said that when you lift things up against gravity, the work you do is basically equal to the gain in gravitational potential energy. Okay, so actually this equation, the work done is equals force over distance, is actually the same equation really as the one we used last week, where GPE equals mg delta h. Now they might not look the same, but if you think, if work done is force times distance, when you lift something against gravity, the force, which is the weight, is equal to the mass times the gravitational field strength, something we did in forces unit earlier. Okay, so if you have a 2 kilogram weight, you times it by g, which is 10, to give a force of 20 newton. So in my brackets here, my mg, mass times gravitational field strength, that's the same as force. And the distance that you're lifting it is the same as the height. So I've turned this black work done equals force times distance equation into this blue one, which basically means the work done is equal to mass times g times h, which is the same as the change in gravitational potential energy. So when the mountain lifts up his weight and he transfers 4,008 joules of energy, he transfers that into gravitational potential energy. So the weights he's just picked up have gained 4,008 joules of gravitational potential energy. So you can work out the energy transferred or the work done in 2 different ways. You can either use the work done equation, which is normally the simplest way, okay, or you can use the gravitational potential energy equation, but essentially they're both the same thing. Okay, so what I want you guys to do is a bit of practice at using these work done and power equations, okay, just to remind yourself of how we used them last year. So what I'm going to do, I'm going to show you, here it is. So in Google Classroom, I've linked this Google Doc, which I'd like you to use, and you are going to calculate your power output doing 3 different tasks. Now the tasks you do are up to you, but during the task you've got to be lifting something against gravity. Now some examples of things you could do: you could run up the stairs in your house, or you could even walk up the stairs if you're feeling lazy. You could pick up any object of a known weight. So if you happen to have like gym weights around, you can use those, but also anything that contains water. So for example, if you're in for lifting heavy things, if you've got like the big water bottles that go on the coolers, you know, like the 19-liter ones, okay, anything that contains a liter of water weighs 1 kilogram. So if you've got 19 liters of water in a bottle, okay, I know that the mass of that will be about 19 kilograms. So every liter of water is 1 kilogram. So you don't have to do it with a huge, great bottle of water. It depends how tough you're feeling. Okay, but you could do it with a 2-liter water bottle, and you could do like repetitions by like lifting weights a number of times. So you're basically going to choose 3 activities that you're going to carry out. Now, for each one, you need to know what the mass is that you're going to be lifting. I mean, if it's lifting yourself, you need to know your own mass. If you don't know it, you can make an estimate. I mean, I know my mass is about 80 kilograms. You know, if you don't have scales in the house and you don't know your mass, you can make something up. But ideally, I'd like you to go and measure it, because this is a science lesson. We do like doing measurements. So you're going to decide on an activity and how many times you're going to do it. Okay, so let's say you're lifting up a bottle of water 10 times. Okay, so you would put in this first column here what the mass that you're going to use is. So let's say I lift up a 2 kilogram bottle of water. I'm going to put that into here. Okay. Now we're doing it on the Earth. So in your table, I've put in that the gravitational field strength is 10 newtons per kilogram. It's always going to be approximately that on the Earth. Now the height of 1 repetition. So you need a tape measure or a ruler here to measure how far you're going to lift something. So let's say you're lifting something from the floor to the top of your head. You would measure at that distance. Let's say it's 2 meters, 20 centimeters. I put 2.2 in. Okay. Now let's say I've decided I'm going to do that 10 times. The total height I'm going to lift would be 10 times as much, so that would be 22 meters. Okay, so you decide how many repetitions are you going to do, what's the height of one repetition, and then you're going to work out the work done. Now, the work done is the same as the gravitational potential energy. I put a little star here to show this. The gravitational potential energy gained will be the same as the work done. So you can work it out either way, either using the work done equation or the gravitational potential energy equation from last lesson. So I would be saying, well, it's mass times g times height, so I would be 2 times 10 times, well, the total height gain I've got to use. So if I've lifted it multiple times, I use that, and I get myself my gravitational potential energy. Now, at the same time, I need to be timing how long it takes, okay? I'm just going to make up that it's taken 4 seconds here, okay? Now, once I know how much my gravitational potential energy is, or my work done is, in this case, what's it going to be? 220 times 2, 440. Okay, I've made the numbers nice and easy here. Then I have to work out the power. I take my gravitational potential energy, which is the same as my work done, and I divide it by my time taken. I've put it in here for you so that you can see. 440 divided by 4 is going to be 110 watts. So I want you to choose 3 completely different activities, okay? One could be you walking up the stairs, one picking up one object and another object, doing different numbers of reps. And I want you guys to fill in this table the calculations of how you work out how powerful you are. Now, obviously, to be very powerful, you need to use energy quickly, okay? So if you do things slowly, like you walk very slowly up the stairs, that's fine. I don't really care, because at the moment I just want to know that you can do the physics. But obviously your power is going to be low if it takes you a long time to use the energy. If you run and do something super quickly, your power output is going to be higher. Okay, so choose 3 completely different activities, put the data in. I'm going to come and have a look and just check that your calculations are correct for these. Okay, so that's the work I've put on there. Okay, if you can make sure you read the Google Classroom instructions carefully and make sure that you complete all the tasks that I've given to you. Okay, right, thank you very much.